Hello world, this is Claudia Roberts, and I will be presenting the online pre-recorded video of our body of research entitled CLIME, Completeness Constrained Lime. My fellow collaborators are Etsham Alahi and Ashok Chandrasekhar. Furthermore, this work is in collaboration with Princeton University and Netflix and was generously supported by United States government funding through the ND-SEG Fellowship. Let's get started. So humans have historically learned through trial and error. When an unexpected event occurs, something that doesn't fit in one's mental model of the world, we ask ourselves, why? We seek an explanation for this seemingly anomalous behavior. We should hold our mathematical models of the world to the same standard. Abnormal events should force us to interrogate the mathematical model and seek explanations through why questions. Algorithmic explanations are useful and necessary. They allow us to detect biases in models, audit the model, consider counterfactuals, debug the model and make it more robust, and can offer guidance for how to improve the model. Movie recommendation is not a low-risk task. To quote, as soon as the model has a significant impact, be it financial or social, interpretability becomes relevant. And economic opportunity is on the line for countless stakeholders in movies, such as the screenwriters, costume creators, actors and actresses, producers, editors. There are a lot of people involved in the movie creation in the movie creation process. And so these are opportunities to make money or to not make money. And also storytelling has the potential to not only entertain, but to build empathy and educate. Algorithmic explanations are useful for improving models and for helping build trust with various stakeholders. Because trust in technology and algorithmic decision makers is not a given in all aspects of our society. And generally speaking, it is well accepted in the industrial Recsys community that explaining recommendations or explanations is crucial if users are to understand their recommendations. So thus, we desire a method for interrogating a learned mathematical model to understand why it is making the predictions it is making in a human interpretable way that gives the end user confidence that the model is behaving in a way that is consistent with their existing beliefs and desires. So LIME is one such framework. LIME gives us a way to do just this. LIME is a popular method for learning local, interpretable surrogate models that can be used to explain individual predictions coming from any machine learning model. And so our first task is we modified LIME for movie recommendation. And we identified a few ways that we can modify LIME for the specific task of movie recommendations, which is what we were interested in. One, we can use importance sampling for weighting. Two, we can use a classification model that is appropriate for ranking policies instead of MSE, which is useful for point estimates. Or three, we can represent the original input into a metadata space. So we just do want to highlight there is a difference between recommender task and other predictive tasks like computer vision, for example. So in recommender systems, where the recommender systems often output rankings of items, and oftentimes you don't even have access to the actual point estimates. And recommender systems operate on movie IDs and binary information. Did the person watch or not watch? Did they engage or not engage? So just as a simplified graphic, you can see you can have a play history, so like a list of movie IDs that a user has watched or interacted with. We pump that information through the recommendation system, and the output is simply a ranking of catalog of movies. So during our exploration of modifying LIME in these various ways for movie recommendation explanations, we observed that LIME doesn't do as well in sparse segments of the dataset as compared to another popular explainability framework called SHAP. So Shapley additive explanations, we'll just go ahead and call this SHAP. Its aim is to also faithfully explain the local predictions of machine learning models. And while SHAP is computationally much slower than LIME, depending on the underlying prediction models, it has some important theoretical guarantees, such as guaranteeing the fair distribution of the prediction across the features. And this property is called the completeness constraint, or what we call the completeness constraint. It has various names in literature. We observed that while SHAP outperforms LIME on aggregate, the two methods behave very differently depending on the sparsity of the data. We evaluate these two popular explanation models based on how they perform when explaining a recommendation for a data instance with very little historical interaction data versus when explaining a recommendation for a data instance with plentiful interaction data. And we found that LIME does better than SHAP in dense segments of the data set, and conversely, SHAP outperforms LIME in the sparse regions of the data set. And this is important because recommendation tasks operate almost exclusively in very high sparsity data settings. So we performed a bias variance analysis and traced this difference in performance to the differing bias and variance characteristics of the underlying estimators of LIME and SHAP. We found that SHAP exhibits lower variance in sparse segments of the data compared to LIME. And we attribute this lower variance to the completeness constraint property inherent in SHAP and missing in LIME. And then we hypothesize that this constraint acts as a regularizer and therefore increases the bias of the SHAP estimator but decreases its variance, leading to a favorable bias variance trade-off, especially in high sparsity data settings. Under the completeness constraint, the explanation is said to have a fair attribution of feature importance as it captures the contribution of each feature in the underlying model's prediction of the data instance of interest. So with this insight, we introduce the same constraint into LIME and formulate a novel local explainability framework called Completeness Constrained LIME, or CLIME, that is superior to LIME and much faster than SHAP. We use a validation split. In terms of our experimental setup, we use a validation split of 10,000 users outside of the training set. And for each validation user, we generated the personalized ranking from the black box movie recommendation model and used the top ranked movie, T sub U, for local explainability. We partition 10,000 validation users into 8 equal sized buckets according to the number of non-zero movie interactions in the feature vector or the view history. We label the data set segment with the highest sparsity as sparsity rank 0 and the lowest sparsity segment as sparsity rank 7. And then in terms of our evaluation metric, we use a delta rank. So given a ranking of non-zero movies in the original feature vector, or the view history, ranked according to the explanation model coefficients, for each validation user, we take the top K input movies according to the explanation model coefficients and remove them from the feature vector. This gives us a modified feature, or a modified view history with the top K most important input movies according to the explanatory model removed. We remove them. We then compute the output ranking from the black box model with this new modified vector as the input. We calculate the difference in the rank of the movie of interest, the top ranked movie, which was the top ranked movie earlier. The idea is that if the movies that were removed from the original feature vector were really important for the black box model to rank T sub U at the top, we should expect to see a big drop in the ranking of the top ranked movie, originally top ranked movie. And we expect the delta rank to be negative if important features are removed, and the magnitude of the drop to be proportional to the importance of features removed. Therefore, the lower the delta rank, the better. So by adding the completeness constraint to LIME, we show that we are actually able to match the bias variance characteristics of SHAP. And then looking at more results, CLIME and SHAP did a better job than LIME at identifying and ranking the features that were most important for explaining the top ranking of the top ranked movie as the available view history data got sparser and sparser. So as we iteratively remove the top K most important features from the data instance of interest, we observed that as we increased the number of features that we removed, the gap in performance between SHAP and LIME in comparison to LIME widened, with SHAP and CLIME outperforming LIME. Both CLIME and SHAP outperform LIME significantly, whereas the difference between CLIME and SHAP is insignificant up to the top 20 features. So this validates our hypothesis that introducing the completeness constraint into LIME does indeed result in improved local explainability. We also observed that integrating the completeness constraint into LIME results in an estimation problem of lower complexity and thus can be solved as fast as LIME, as seen in the computational analysis below. So as I mentioned, we divided our movie recommendation data set into 8 equal size groups based on sparsity. So based on the amount of interaction data each data instance had. We compared the 3 explainability methods according to sparsity using the 8 segments. We see the expected outcome. The overall delta rank improvements come from the sparse segments of the dataset, where CLIME and SHAP outperform LIME. We attribute this improvement to an overall favorable bias variance trade-off, especially in the sparse segments of the movie lens dataset. We observed that SHAP and CLIME significantly outperform LIME in the sparsest groups, and that LIME continues to outperform SHAP and CLIME in the densest groups. So to summarize, we provided motivation for why explanations for recommender systems require special consideration. We showed the shortcomings of LIME, a popular, easy-to-use explanation method. We showed the shortcomings LIME, a popular, easy-to-use explanation method, had in addressing the needs of recommender systems, which often operate in high sparsity data settings. And we traced the root of the issue to an important property that is found in another popular but slower explanation method, SHAP. We incorporated this property into LIME to create a novel explanation framework called CLIME. And finally, we showed that CLIME is superior to LIME in high sparsity data settings, is as fast as LIME, much faster than SHAP, and is as easy to use as LIME. We hope that you enjoy using CLIME. Thank you.